This is the second video in my series on alternating current. In this video, we are going to look at sinusoidal RMS waves. You will find this topic along with others in my course entitled Basic Fundamentals of AC Circuit Analysis. You can access this and my other courses on my Stan Store at this web address. The alternating current, or AC power, AC voltages, and it seems like a misnomer to call a voltage alternating current or AC voltages, but there is a tendency to refer to anything in regard to producing alternating current as AC. So anyway, it's going to be helpful to understand what these AC quantities look like, and generators of AC quantities or AC power, ultimately AC voltage and AC current, are designed in a special way such that the voltages, the open circuit voltages produced by these AC generators and the current follow what is known as a sinusoidal waveform. And sinusoidal waveforms lend themselves to trigonometric functions that help in the analysis of AC circuits. So we're going to look at the structure of AC voltages and AC current now, and they are referred to as sinusoidal waves. We are then going to look at what those AC quantities mean in terms of the power they are capable of producing, and we're going to define a term relative to these sinusoidal waveforms called RMS values, and RMS stands for root mean square, but we'll get into the explanation of that in a few slides. As I said before, an alternator is designed to produce AC voltage in a specific shape over time. The voltage switches polarity over time, but does so in a very practical manner. When graphed over time, the wave traced by the voltage of alternating polarity from an alternator takes on a distinct shape known as a sine wave, or we can describe the waveform as sinusoidal. In the voltage plot from the electromechanical alternator, the change from one polarity to the other is a smooth one. The voltage level changes most rapidly at the 0 point or the crossover, and most slowly at either of the peaks. Because this is repetitive, we describe the waveform in terms of cycles, where one cycle is made up of 360 degrees. Here we have plotted a sinusoidal waveform over time, and that waveform varies over time, but what we're doing is taking a snapshot of it right now, if you could visualize that, and we're going to state that the sine wave begins at 0 degrees and it starts its rise. So 0 degrees is the beginning of the cycle of the wave, could be voltage or current, and the voltage or current at this point is 0. At 90 degrees, which is a quarter of the way through the waveform, the voltage or current is at a maximum, and for convenience purposes, we're saying it is 1. At 180 degrees through the cycle, the waveform comes back down and goes through its crossover point, and at that point, the wave voltage or current is 0 once again. At 270 degrees, the waveform, voltage or current, is at a negative maximum, and at 360 degrees, we've gone through one complete cycle, and essentially we're going to start all over again. So the angle is 360 or 0 degrees, and we are once again back at 0. If we were to follow the changing voltage produced by a coil of an alternator from any point on the sine wave graph to that point where the sine wave shape begins to repeat itself, we would have marked exactly one cycle of that wave. This is most easily shown by spanning the distance between identical peaks, but may be measured between any corresponding points on the graph. The degree marks on the horizontal axis of the graph represents the domain of the trigonometric sine function and also the angular position of a simple two-pole alternator shaft as it rotates and produces the AC quantity. Since the horizontal axis of this graph can mark the passage of time as well as shaft position in degrees, the dimensions marked for one cycle is often measured in units of time, most often seconds or fractions of a second. When expressed as a measurement, this is often called the period of a wave. The period of a wave in degrees is always 360 degrees. But the amount of time one period occupies, of course, depends on the rate voltage oscillates back and forth. A more popular measure for describing the alternating rate of an AC voltage or current wave than period is the rate of that back and forth oscillation. This is called frequency. The modern unit for frequency is the hertz, or abbreviated Hz, which represents the number of wave cycles completed during 1 second of time. In North America, the standard power line frequency, as I said before, is 60 Hz, meaning that the AC voltage oscillates at a rate of 60 complete back and forth cycles every second. In Europe, where the power system frequency is 50 Hz, the AC voltage only completes 50 cycles every second. A radio station transmitter broadcasting at a frequency of 100 megahertz generates an AC voltage for transmission oscillating at the rate of 100 million cycles every second. Prior to the canonization of the Hertz unit, frequency was simply expressed as cycles per second. Older meters and electronic equipment often bore frequency units of CPS, or cycles per second, instead of Hertz. Period and frequency are mathematical reciprocals of one another. That is to say, if a sine wave has a period of 10 seconds, its frequency will be 0.1 Hertz, or 1/10 of a cycle per second. Frequency in Hertz equals 1 over the period in seconds. This video is part of my Electrical Technical Information series. In this series, I'll be covering essential topics to help you understand electrical systems. Be sure and stay tuned, as I will also, from time to time, be reviewing electrical products that, in my opinion, are worthy of paying attention to. This address will give you access to the supplier of the aforementioned type products. It is also a connection to obtain a free copy of my 24-page 3-phase transformer workbook, which will serve as a quick reference and reminder of technical calculations that you may need. This address, of course, is case sensitive. I'll spell it out and make sure that you have it right. Everything up to the first number is lowercase. That is, lowercase https://bit.ly/3, then uppercase U, uppercase G, a lowercase j, uppercase B, uppercase I, and lowercase g. One of those amazing and versatile products is the 𝐃𝐈𝐒𝐂𝐋𝐀 Delta Pro Ultra, which can be modified to suit any homeowner's needs, operating virtually silent, and when paired with the 𝐃𝐈𝐒𝐿 Smart Home Panel 2 is extremely versatile. The 𝐃𝐈𝐒𝐿 Home Panel 2 ties any and all of your standby power equipment together and will control them efficiently. It will even control your connection to the utility grid to make sure you're only using the least expensive power, switching to your standby power during those expensive time of use rates. In order to view the full range of 𝐃𝐈𝐒𝐿's products and obtain a free copy of my 3-phase transformer workbook, check into this web address and simply provide your email address, which will guide you to browse the full extent of their products. There is no cost or commitment for viewing, and by providing your email address, it will allow me to keep you posted on future videos, courses, and 𝐃𝐈𝐒𝐿 products. Before I end this video, I want to repeat the connection to obtain a free copy of my 24-page 3-phase transformer workbook, which will serve as a quick reference when working on my courses and quizzes. It is also a handy reference and reminder of technical calculations required in your daily job requirements. Finally, here is the link to all of my electrical courses, which are located in my stand store.